Well, greetings, salutations, all nice things. Welcome to our first lesson of Topic 2, where we're going to be looking at exponential and logarithmic functions. One of those words maybe we've seen before, logarithmic, might be a bit more new. I guess you've probably seen the word functions as well. Today, we're looking specifically at exponential functions, just the parent functions themselves and their characteristics. So the parent exponential functions are of this form, where we have, well, we've got our variables y and x. How are they related? X is the exponent of some base. It's some constant value. Now it has to be positive, and it cannot be 1. Reasons being that x can take on any real number. So yeah, it could take on like 1 or 2 or 7. But it could also be 0.5, and it could be negative 1/3. X could be any of those values. And if you have a base like negative 3, then you're talking about a function like this. And if x is 0.5 in that case, then you're talking about negative 3 to the power of 0.5, which is not a real number, unfortunately. So we're only dealing with values of c that are positive and not equal to 1. Those are our options. Take a moment, take a look at these functions here. See if you can identify which ones are exponential. I'm going to do that right away, but just pause the video, see what you can do. So this first one, yes it is. It's just y equals some base to the power of x, and that base is positive. It's not equal to 1. So that's a yep. This one's not. The base is not a constant. And x isn't in the exponent either. This one, we have a negative base. This one's okay. Here, this one directly violates this rule of c is not equal to 1. And again, here, base is not a constant. In this case, c is equal to 0, which is not greater than 0. It's a weird number, but this one is okay because it's some positive non-1 value for the base. And then this one, we don't even have an exponent. This is not even a power. So of all those examples, only 3 of them are exponential functions. Again, recognizing this specific form. We're going to graph a few, or 4. We're going to graph these on the same set of axes, and then we'll talk about what we notice about these. Of course, for graphing, we should make sure we label our axes, and we should probably label our scale at some point as well. This could probably be a 1. 1, 2, 3, 4. Let's call this a 5 up here. So each tick mark is just a 1. Now we've never graphed these before, so how in tarnation do we do that? If you want, you can use just a table of values for starters, and we'll just pick a few of these. So like, let's see, let's go negative 1, 0, 1, and 2. And we can do that for each of them. For y equals 3 to the x, we can make a table of values. And we'll do that for all of them. So you can take a moment, see if you can fill that out. And then once you're done, plot the values, play connect the dots, see what you get. course, as I jump into things, here we go. If x is 2, y is 2 to the power of 2, so that's 4. If x is 1, y is 2 to the power of 1, which is 2. If x is 0, y is 2 to the power of 0, which is 1. And if x is negative 1, y is 2 to the power of negative 1, which is just 1/2. And we could similarly fill all these out. 3 to the power of 2 is 9, 3 to the power of 1 is 3, 3 to the power of 0 is 1, and 3 to the negative 1 is 1/3. So we just keep doing that. And now we can plot these. So I'll use something bluish for this first one. We've got 0, 1 on here. We've got 1, 2, and we've got 2, 4. If we wanted, we could even go further. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So these are just all powers of 2. And then going the other way, we're at like a half. And when we play connect the dots with this, of course, using nice kind of sketchy lines, not just doing this all in one swoop. Gotta do this as if we care about how it looks, which I kind of do. And we go to like a quarter, and then we go to like an eighth, and then like a 16th, and then a 32nd. This thing gets real tight into 0. And of course, at the other end here, it just explodes because we have 16, and the next one would be 2 to the power of 5, which would be 32. After that, we have 64, 128. This thing is just massive. That's y equals 2 to the x. Let's try another one. So y equals 3x, we'll do in purple. Again, just plotting all the points we see. 7, 8, 9. How high does this go? 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 27. Way up there. And we'll graph another. Oops. Alright, so our last one was 3 to the x. Next up we have 4 to the x. And we'll keep going here. 9, 10, 11, 12, 13, 14, 15, 16. Here. Sure, this other blue will do. So for y is 5 to the x. Again, just plotting things from the table of values. We got that 0, 1. We got 1, 5, and then up to 25. I think is right here. So if we look at these functions, we should kind of notice some things. Firstly, I notice that they all have this one same common point. They all have the point 0, 1. And that's because if you take any positive value to the power of 0, you will get 1. So all these parent exponential functions will contain that point. Other thing worth noting is that they are all completely positive, that they never go above the or below the x-axis. In fact, what we have there is a horizontal asymptote, a trend line that it kind of guides towards that on the left side. On the right side, that trend doesn't really matter, but on the left side, we have the line y equals 0 that these functions try to get closer and closer to. They never quite reach it. Even if we go to like x equals negative 100, well, if it's y equals 2 to the x, then y equals 2 to the negative 100, which is 1 over 2 to the 100. It's really close to 0, but it's not quite 0. So as we go further and further left, we'll get infinitely close to 0, but never quite reach it. Therefore, these things are always positive. And then we also see that they're also always increasing. As we go left to right, it just goes higher and higher and higher. So there's never a wave before it goes up. Any point is always higher than the one before it. Those are all very exciting things. Let's see if there's anything else I actually noted on this next page. Oh yes, and of course, the larger the base, the more sharply this function grows. So here we had 2 to the x, but then 3 to the x was a bit more rapid, 4 to the x was more rapid than that, and 5 to the x just started to rocket right up there. So those are things we notice. And then of course, as also stated on the next page, is this collection of points. So we already noted that they all have the point 0, 1, but they also have the point 1c. So whatever that base value is, that's the y value when x is 1, because anything to the power of 1 is just itself. I'm going to try graphing these ones as well, and just for the fun, I'm going to choose some different values of x. I will still label my axes. So this is 5. But I dare you to give it a try. I'll be a bit less explainy on this one, but in case you want to know what values I'm going to choose those ones. Oops. I'll plug those in and see what happens. When we have 1/2 to the power of negative 2, that's actually the same thing as 2 to the power of 2. Hence, I'll just put a 4 there. And similarly, 1/2 to the power of negative 1 is just 2. Anything to the power of 0 is 1, and anything to the power of 1 is just itself. And I'll similarly fill in the rest of these tables. Anything to the power of 0 is 1. 1/3 to the negative 1. Well, to the power of negative 1 says take the reciprocal. And then to the negative 2 says take the reciprocal to the power of 2. So that's where all these values are coming from. And I can once again plot these. So this one I'll do in blue again. Negative 2, 4. Negative 1, 2. We're dealing with those values. And if we want, we could even get more. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And as usual, when we play connect the dots, play it like you mean it. So it should be a nice gentle curve here. And our curve actually goes through all the points that we have. All right, there's 2 dx. Or, oop, that's not 2 dx. It's 1/2 to the x. And let's just get the others in here. Is that high before? 5, 10, 15, 20, 25. Okay. It's worth noting that even though these things start to rocket up real quick on one side, they'll never have an infinite slope like that, or an undefined slope. They could be like highly more valuable than the term before them, but never infinitely higher. There's always going to be some value between 2 other points that we can actually identify. That, and then finally this, that. Where am I at? 9, 10, 11, 12, 13, 14, 15, 16. And things we note there. Again, we still have this point 0, 1. So all these parent functions, no matter what the base is, as long as it's valid for an exponential function, we'll have that point 0, 1. We do still have the point 1c, it's just kind of weird to see. See. And then at -1, we have the reciprocal. In fact, what we notice is these happen to all be horizontal flips on these other ones. If we took these and we did a reflection over the y-axis, we'd just get these ones in there. I wonder why that is. Nice little mysteries, I guess. And then these all still have this horizontal asymptote. So even though the bases are reciprocals, it doesn't mean that we're going to negative land. So we still have this horizontal asymptote at y equals 0. And yes, even though it's the axis, you do still have to include that equation next to it to indicate that that's the equation of that asymptote. And these graphs are perpetually decreasing, so they go down from left to right. There's never any wiggle in there. They never level off and then go back down. It's just always going down. Going down at a decreasing rate, but going down, which is just a result of the reflection from the first page. So let's talk about all exponential functions. So anything of the form y equals c to the x, where again, c has to be positive, but it's not equal to 1. There is a There is a horizontal asymptote at the line y equals 0. The graph will always contain 2 key points, 0, 1. So a very distinct, like, literal point for all of them, and then 1c. And if you're dealing with fractiony fractions, if you want, you can also talk about the key point at -1, 1 over c. That way you get a nice, potentially whole number out of it. if c is greater than 1, we will have an increasing function. And if we're less than 1, but still positive, of course, then we're always going down. How many x-intercepts? Well, we never actually hit the x-axis anywhere. Not there, and not there. So the number of x-intercepts is going to be 0. So without transformations, and we'll get to transformations at some point, we can use those key points to determine this function's equation. There's stuff we can figure out about what's drawn here, and then we can talk about if it's representing exponential growth or exponential decay, where growth is where it grows, decay is where it decays, it goes down. So this one here contains the point 0, 1, but they all do. What happens when x is equal to 1? Ooh, I don't know what value that is. What about at negative 1? Ah. So we've got the point negative 1, 5. So if we're talking about y being c to the power of x, that means 5 is equal to c to the power of negative 1. And if that's the case, we'll take the reciprocal of both sides. 1 over 5 is equal to c. And that makes sense because this thing is going down. Because it's always decreasing, we know that c has to be between 0 and 1. So this value makes sense, and we can just straight up say that y is equal to 1/5 to the power of x. And this represents exponential decay. And this other one, well, that's interesting. All right. Honestly, I don't even see a nice value out of that, but we'll see what happens. Like, this looks close to 1.75, but I can also tell it's not quite there. But this, that's a nice point. We've got that point at 2, 3. Okay. Well, y is c to the x. So 3 is c to the power of 2. Ah, I've got to take the square root of both sides. Oh, that wasn't a very pretty number at all. Interesting. In fact, root 3 is about 1.71-ish, which I guess makes sense because of, not there, but this point we were seeing here. So it wasn't actually as exact as I thought. It was not 1.75. So any positive real number can be a base. In this case, that positive real number isn't the prettiest number in the world, but we still love and respect root 3 nonetheless. So y is root 3 to the power of x. And this represents growth. There is some practice work. I recommend you give it a go, give it a try, give it a stab, give it a whirl, see what happens. Thank you for viewing this whole thing. Believe in yourselves, believe in the dream, and say hello to someone today. The end.